Hello and welcome to the Kentik video series. In this video, we will be discussing the basics of network and interface classification and how they provide additional means for classifying traffic flows in your network. These classifications will give you additional methods by which to look at your flow data throughout the many components of the Kentik platform. The topics that we will be covering in this video include an overview of network classification, what it is and how it's configured, a look into what Kentik calls network boundaries and how they are defined, and then applying that to understand how interface classification works and is configured. Configuring your network classification is the first way in which we start to define what Kentik will see as being internal to your network by defining IP ranges and ASNs which you want to be considered to be inside your network. To configure the network classification within the Kentik portal, we first navigate to the Admin section, and then on the left menu bar we will click on Network Classification. Within the Network Classification section of the portal, we are able to define IP addresses and ASNs that we want to be considered internal to our network. Within the Internal IP section, we can specify both IPv4 and IPv6 CIDR blocks of IP ranges. There is also an option to automatically include a predefined range of IP addresses, including RFC 1918 IP space, and the full list is viewable by clicking on the question mark next to the option. Within the Internal ASN section, we can also do the same thing and add any ASNs that we want to be classified as inside of our network. We also have the option to automatically include private ASNs as being internal to our network. Both the automatically include private IP and automatically include private ASNs options are selected by default. Once you have added your IPs and ASNs to these lists, you can click on the Save button to save your changes. The purpose of network classifications is to give your flow data additional dimensions, which can then be used to give your traffic an enriched definition of where traffic flow originated and terminated, and then to give it a profile based on where it originated and terminated. The traffic origination and termination dimensions of your traffic flow are based on both the source and destination IP and ASNs of a flow. They are considered to have an inside traffic origination if the source IP or ASN matches what you have set up in the network classification to be internal. Otherwise, they are considered to be outside. The traffic termination dimension works the same way, but examines the destination IP and ASN and considers the traffic termination to be inside if it matches the IP address or ASNs that are defined in the network classification to be internal. Otherwise, it's considered to have an outside traffic termination point. The traffic profile dimension is derived from the traffic origination and termination and adds directionality to traffic flow into the following categories. Through traffic is traffic that is coming from outside of the network and terminates outside of the network. Sometimes known as transit traffic, it is traffic that has an origination and termination dimension that is outside, or traffic that has a source and destination external to your network. Ingress traffic is traffic that is coming from outside of your network but terminates inside your network. It has a traffic origination of outside but a traffic termination point that is inside. Traffic with an internal traffic profile is traffic that has a source and termination dimension that is set to inside. Egress traffic is traffic that originates within your network or inside, but terminates somewhere that is defined to be outside or external to your network. Before we dive into interface classification, we need to answer this question: what are network boundaries? Kentik defines a network boundary as being either internal or external, and is based on the source and destination interface of the traffic flow. If we look at the diagram on this slide, you can think of the points within AS100 as being your company's network. You may have devices with interfaces sending flow data to Kentik that are at the edge of your network, where they interconnect with networks outside of the domain which you consider to be your own network, and those are considered to be external. Likewise, you may have devices with interfaces sending flow data to Kentik that are connected to other networks inside of your own domain, and those are considered to be internal. Looking at the diagram, we can see how there is a traffic flow from AS222 to AS444, which goes through our AS100. As traffic comes into AS100 from AS222, the source interface of the traffic flow would be defined as being external. Since we view traffic that originates outside of AS100 to be external, and the destination interface of the traffic flow would be internal, since we are sending that traffic to a router that is inside of AS100 on its next hop. So at this router, or observation point, the traffic flow has a source network boundary of external and a destination network boundary of internal. Traffic then flows from our edge device to the next router in its path. At this second router, which is in the middle of our AS100 network, the traffic that originated at AS222 comes into an interface which is connected to a router that is within our network, so we see the source interface as having an internal network boundary. That same traffic then flows out towards the next router, and we see that the outbound interface for our traffic flow also faces a device that is internal. So at this router, or observation point, the traffic flow has both a source and destination network boundary of internal. At the last router that the traffic from AS222 to AS444 transits through the AS100 network, it enters the router on an interface which faces the inside of our AS100 network, and then exits towards AS444 out of an interface which faces the outside of our network. At this router, or observation point, the source network boundary of the original traffic flow would be internal, but the destination network boundary of the traffic flow would be external. By adding these network boundaries to this and other traffic flows, we are able to avoid duplication of flow data counts, as we can separate traffic based on its network boundary, and then classify the first hop in this traffic flow as having a source network boundary of external and a destination network boundary of internal. The second hop then has a source and destination network boundary of internal, and the final hop has an internal source network boundary, but an external destination network boundary. With this understanding of what network boundaries do, let's examine how they are used by the interface classification component of Kentik to create even more dimensions by which you are able to enrich your flow data. As we have discussed before, the network flow data that is collected by your devices is unidirectional in nature. The flow data itself will contain only the ingress and egress port for the device on which it is sampled, so traffic flow data doesn't have any awareness of which port is internal or external within a given network. Interface classification lets us create a matching engine with classification rules in order to map interface names or descriptions or IP addresses into usable network boundaries and connectivity types. Within the Kentik portal, under the Admin section, we navigate to the Interface Classification menu on the left-hand side to bring up the Interface Classification section. First, let's look at how we can set up our default interface classification options by clicking on the Configure Interface Classification button in the upper right corner. The General Settings portion of this menu lets us determine which interfaces should be excluded from being classified. If we want to exclude any interface that doesn't contain an interface description, obtained either via SNMP or manually set for the interface, we can toggle Exclude Interface with No Description. We can do the same if we only want to classify interfaces which are assigned an IP address by toggling the Exclude Interfaces with No IP Address option on or off. If both options to exclude interfaces with no description and exclude interfaces with no IP address are toggled on, then we can also select if we want to set an or an and statement between these to say that we want to exclude interfaces with no description or interfaces with no IP address, or to exclude interfaces with no description and no IP address. The option to exclude host, nprobe, or kprobe interfaces should be toggled on unless you have those types of instances configured and you want to classify those types of interfaces. In the next section of the menu, we can see where we have network boundaries defined for different interface connectivity types. Initially, the network boundary will be set to a Kentik default value for what we have found is most commonly the boundary for certain types of interface connections. You can change the default value of any of these connectivity types, and the default value can also be overridden when you set up an interface classification rule. Before we look at setting up interface classification rules, let's go over the different connectivity types that are defined in this screen in order to give you a better understanding of how to apply them when you begin to set up new rules. The overall purpose of the interface classification is to add 2 more dimensions to our traffic flows based on their ingress and egress interface location on a device, both a network boundary and also a connectivity type. As we just saw, there are quite a few different connectivity types, so let's take a quick look at each so we can appropriately apply them to the interfaces within our network. Transit interfaces are those which connect to an upstream internet provider. Usually, these connections contain a full BGP table from that upstream provider, but depending on your setup, they may be a partial BGP table or even a default route from an upstream provider. These connections have a default network boundary of external. Free private peerings are connections that are generally to an individual upstream provider, many times to a content or service provider, in order to provide settlement-free peering between your network and theirs. These too have an external network boundary by default. Paid private peerings are the same types of connections as their free counterparts, except these peerings are generally attached to some sort of payment, either for a flat or metered level of traffic exchanged, and also have an external network boundary by default. IX, or Internet Exchange Peerings, are connections to a public peering facility, which contains a fabric that allows for multiple inter-AS peerings between providers at a centralized location over a single interface or bundle of interfaces within a device. The network boundary for these connections are external by default. The next 2 connectivity types are data center and aggregation interconnects. Data center interconnects are typically connections used to connect devices together within a single data center. Sometimes also thought of as backbone connections, this particular classification is meant for cases where a data center team and a backbone team coexist and one is a customer of the other. Aggregation interconnects are usually applied to a bundle of interfaces between 2 devices that are on separate levels of aggregation, typically found in hierarchical data center switching or routing topologies such as leaf-spine. If there's no need for a specific distinction in this regard, they could alternatively be classified as backbone. Both data center and aggregation interconnects have an internal network boundary by default. Embedded cache connections are used in cases where interfaces are connected to a cache appliance, which are typically provided by a CDN or content provider. Some examples of this are Netflix OpenConnect, Google Global Cache, and Akamai caches. They are embedded within an ISP's network to provide content locally that can be cached in order to save on transit or upstream provider bandwidth, as the content is generally static in nature and the content is generally refreshed via a proxy feed during off-peak hours. And since they are contained within your network, they have an internal network boundary. Backbone connections are a general term for connections which are between 2 devices within the same network, whether or not they are within the same data center. In networks which have separate backbone and data center teams, the backbone connections are typically outside of the data centers, while using the data center and aggregation interconnect types within a data center for connectivity type classifications. These also have a network boundary of internal by default. The customer connectivity type is used for interfaces that generally point towards a downstream customer of your network. These normally also contain a BGP peering to send either a full or partial BGP routing table from your network, and are generally connections which are revenue generating for your company. They have an external network boundary by default. A connectivity type of host is used to indicate a direct connection between a router and a server host within your network or within a data center, and have a network boundary of being internal to your network by default. Available and reserved connectivity types are used for interfaces that are not currently in use within your network. Available interfaces are those which are not currently reserved for any type of future use, while reserved indicates that they are allocated for a future use, and both have a network boundary of internal by default. There is also a classification type called Other, which can be used as a catch-all for interfaces within your network for which no other connectivity type described applies. Back in our portal, since we have not defined any interface classification rules, we'll click on the Add First Rule button in order to set up our first interface classification rule. In the Add Rule screen, we see that on the left side we have two sections, an If section on the top in blue, and a Then section below it in green. The If section is where we configure the conditions that we want to match upon. We can click on the drop down to see that we can match based on either interface name, interface description, or interface IP address of an interface. The next drop down allows us to select the operator which we want to use. If we want to match either the interface name or interface description, the operators we can select are equals, meaning that there must be an exact match based on the criteria you specify, contains, meaning that the interface name or description must contain at least what is specified for the criteria, or matches regex. Matches regex, or regular expression, can be used to specify a regular expression and to create capture groups which can be used within the provider settings to create provider classification as well. If an interface IP is specified, the operators which we can select are different. We can use either isInSubnet and specify an IP subnet to match upon. We can select isPublic or isPrivate IP address to match against either all public or all private IP address ranges, or we can select has no IP address if we want to create a rule that classifies all interfaces which have no IP address assigned to them. The next portion of the If section is where we can decide which devices we want to apply the rule to when it runs. In most cases, you'll probably use all devices, but if you want to either select specific devices to be included or excluded from a rule, you can click on the Edit Included or the Edit Excluded devices and make selections from those screens. The bottom Then section is where we decide how we want to classify interfaces which match the rule we have created. First, we select the connectivity type we want to be applied to the interfaces that match our rule. By default, the network boundary that will be applied will be the default that is selected for that connectivity type, but we can toggle the auto option off if we wish to change the network boundary to a different value. You'll notice that there is also an option to change the network boundary to none, meaning that you want to give it no network boundary value if it is classified by this rule. The provider section can be used in two ways. If you create a rule and you know that any interfaces which match this rule will only connect to a specific provider, you can specify that within this field, and an additional provider classification will be applied to the interface, adding another dimension to your traffic flow. Also, if you're using a matches regex operator, you have the ability to use a capture string to use a portion of the regex as the provider. This can be useful if you have a standard format for your interface description and specify a provider within it. Let's go ahead and set up an example. We're going to set a rule that matches the interface description using the matches regex operator. We can see a list to the right of all of our unclassified interfaces. We want to create an expression that will match on the regular expression local provider, and then in parentheses use a catch-all. We want to look at all of our devices when this rule is run, so we will leave the included devices to select all devices. For the connectivity type, we're going to go ahead and set this to transit because we're going to say that these are transit connections. We'll leave the network boundary set to auto as we know that these are all external connections. And in the provider field, we will use the $1, which will take the information that is in the parentheses in the regex expression and populate that within our provider field. Down at the bottom, we have an option to test this rule, which will run it against all of our interfaces that are currently set up on our devices. Let's go ahead and click this and see what happens. Now we can see that there's an Interface Matches tab at the top, which will contain all of the devices along with interfaces that match the rule that we have configured. If we click on the device, we can see those matches and how they were classified. We can now see the interfaces which matched our rule, and if you notice, the provider column for each of the interfaces is set to what was contained within the parentheses for our matches regex. You can create much more complex regex matches, but this gives you a basic overview of what is created by using this method. Once you've created the rule, you can click on the Add Rule button, and now this interface classification rule is added to your list. Each time you create or modify a rule, you will need to run an evaluation to reclassify your interfaces. This will be indicated at the top of the screen, and you can click on the Run Evaluation button to do so. On the right side of the screen, we can see the percentages of interfaces that are classified across all of our devices, along with the total number of devices, interfaces, and classified interfaces across all of our devices. You can also click on the View Unclassified Interfaces button to view a list of interfaces which are not classified by any rules. Many of the pre-configured dashboards will require you to have at least 80% of your interfaces classified before they will return accurate results. Also, any component which uses things such as connectivity type or network boundary as a dimension will not return information for your traffic flows based on those dimensions until the interface classification is completed for all of your device interfaces. One additional thing to consider when you are setting up your interface classification rules is that as you create more and more rules, they are evaluated in a top-down order. This means that if you have multiple rules, you will want to order them from most specific to least specific match, with a catch-all rule usually at the bottom of your list. When a new rule is created, it will be placed at the bottom of this list. You can always reorder the list by dragging the rule to a new place in the order and then running the rule evaluation after doing so. This concludes our training session on network and interface classification. Thank you for watching.